Hi guys, welcome to another CNCM member lecture presented by yours truly, Arnav Adhikari. So let's get started. So here's some background knowledge. You probably want to read this from EGMO by Evan Chen, the inversion chapter. It's really helpful. It helped me get all the knowledge that you're going to learn in this lecture. So go ahead, check it out. It has loads of information that's helpful. This presentation is going to be like the same information as that, same numbering of theorems and lemmas as well, so you should check that out. And then also, before you start learning inversion, first note that inversion is actually a big topic in Olympiad geometry, so this lecture helps with that. In addition, as AMIs get more modern, you're going to see a lot more geo problems in the final five that become more Olympiad styled instead of some like bashy problems that you could easily bash. And so it's important that you start learning more advanced synthetic techniques, especially those in Olympiad geometry. So inversion is going to be helpful. Now, that being said, it's not, you don't need it for AMI. It's definitely helpful, but it's not necessary. And if you feel that this is going to be too hard, don't worry. You don't have to watch this. Learn other topics before you come back to this. Don't worry. So, continue if you want, but don't feel too bad if you don't understand, okay? Alright, so let's get started. So, oops, sorry about this jumbling. We're going to start with the definition of inversion. We first begin by adding this special point to the plane called the point at infinity. So now an inversion through a circle omega with center O and radius R is a map that goes as follows. The center of the circle, which is O, is going to be mapped to the point at infinity, and vice versa. The point at infinity gets mapped to O. For any other point A is going to get mapped to a point A prime on ray OA, so that OA, the distance OA times the distance OA prime is equal to the radius squared. So now by this, it's easy to see that an inverse of a point is the point itself. Now going back to this O and P and sub infinity, so we know O is 0 and O P infinity is essentially, you could say, infinity. So when you sub that in here, O times O P infinity, it's almost as if you're dividing by 0 or infinity. So I know that's not exactly such a helpful tip for memorizing, but just if that helps you remember, go ahead. But either way, it should still be pretty intuitive that O is going to get mapped to the P point at infinity and vice versa. Now, as a consequence of this, we can easily see the following. Lemma 8.1, inversion and tangents. Let A be a point inside omega other than O, and let A asterisk be its inverse. Then the tangents from A asterisk to omega are collinear with A. So those are the tangency points, and then that's A asterisk, and that's A. So it's not hard to prove. It's just similar triangles. You can try proving it by yourself, but it's just, you can draw the radii here, and then notice there's some similar triangles. So pretty easy to go. Let's continue. So we found the inversion. Okay, we know this. Ooh, wow. What is this going to help us with? Well, here is the first major consequence. Now, we see that this OA times OA asterisk equals R squared. That looks like power of a point, right? So indeed, it causes a cyclic quadrilateral to form if we look at 2 points at a time instead of 1. So because of power of a point, OA times OA asterisk is equal to R squared, and by definition, that's equal to OB times OB asterisk. So that means A, B, B asterisk, A asterisk is cyclic. Now, that's pretty useful, right? It gives us an angle condition, you can see here. So we can see that directed angle of OAB OAB is equal to the negative of the directed angle OB prime A prime. Now, the reason it's negative is because it's in directed angles. We're gonna have the order is causing the negative. So negative OB prime A prime is the same as A prime B prime O prime positive. So that's directed angles. Now, if you're not comfortable with directed angles, you can just ignore this directed angle sign and the negative to just find that plane angle OAB is equal to OB prime A prime. But directed angles are actually pretty important when you come with configuration issues, especially in Olympiad problems. So it would be helpful if you got used to this. So you should try checking out one of Evan Chen's handouts. It's right here. Alright. Yeah, so that's our very first consequence, an important consequence of inversion. Now let's continue. Okay, so we have this. Now this also helps us with three new very important things. These are the fundamentals of inversion. These are the things that help us realize what an inverted diagram looks like when we invert a problem. So there's three cases. A cline, so to sum, a cline inverts to a cline, where a cline is just a circle or a line. So specifically, our first case is that a line through O, the center, inverts to itself. The second case is when we have a circle passing through O, it's going to invert to a line. That line doesn't pass through O, but the important thing is that the diameter of the circle containing O, like the line of the diameter of the circle containing O, is perpendicular to the circle's image. And the third case, a circle that doesn't go through O actually inverts to another circle not through O. But now note that these centers don't exactly invert to each other, but the centers are collinear with O. So I'm not going to provide a full proof. You can actually check out the proof in Evan Chen's handout, or like in EGMO, same thing. But a couple sketches here. So part A, it's true by the definition of inversion, right? Because points are inverted to another point on the same line as the line connecting the point and the center. So each point on this line is going to get inverted to another point on the line, and so that line remains constant. For the second case, we're using angles along the line. So for example, we have A, B, C collinear points. OAB angle, directed angle OAB is equal to directed angle OAC. Now, we're going to show now that the line gets inverted to a circle, and then now, because of theorem 8.2, we can actually find the angles between these inverted points, and then we can show by cyclic quadrilaterals through angles that the line's going to become a circle, given points on the line going to inverses on the circle. And now for part C, we can consider an arbitrary point on the circle, use theorem 8.2 to show the angle theorem, to show that its inverse lies on the circle with the diameter formed by the inverses of the original diameter, and inverses of the endpoint of the original diameter. So that's also just mainly similar triangles. Yeah, it's also important to note that the centers don't invert to each other. They're only collinear, but still, the fact that they're collinear is pretty useful. Let's continue. Oh wow, there's more. So an important thing to note is that inversion indeed preserves tangencies. So if two entities are tangent to each other at a point, then those images of those entities under inversion are going to be tangent at the point's inverse. Okay, so that's actually pretty helpful. Now, let's say we had two circles, they pass through some point O. If we invert it through O, it turns out that those circles become lines. But because of this part that, where is it? The diameter of the circle containing O is perpendicular to the line. Because of this tangency condition, we actually see that these lines become parallel. Now this is very, very helpful. We're turning these circles into lines, and parallel lines, which is more special. We know a lot more about parallel lines. So that's a very important thing to know about tangency. And preserving tangency is also very helpful. And then just like tangency, inversion, intersections are preserved as well. This is very important as well. It helps us, draw the diagram, make some important observations, etc. The next couple slides are going to contain a couple lemmas that are direct consequences of these tools, and they're important in some inversion problems. And I promise I have proofs here already, actually. So our first one is lemma 8.9, where we invert the orthocenter. Let ABC be a triangle with orthocenter H and altitudes A, D, B, E, C, F. Perform an inversion around C with radius C, square root of CH times CF. Then A and E are inverses, B and D are inverses, and H and F are inverses. Let's draw the diagram. Oops. Mind my sloppy drawings. So that's A, B, I probably should have drawn C at the top there. A, D, B, E, C, F, D, E, F, and that's H. Alright, so we're going to perform an inversion through C over here, and radius, the square root of CH times CF. So first, let's show that H and F are inverses. Well, this is pretty obvious, right? CH times CF. So H prime, CH prime times CH is CH times CF. So CH prime equals CF. And so it's either H prime is over here or it's F here. But that only applies to negative inversion. Don't worry about that right now. Just, it should be trivial to notice that H prime is F. Now, A and E and B and D are inverses. This is actually also pretty easy to show. We have this cyclic quadrilateral AEDB because of these right angles. So using power of a point, since CEA are collinear, CDB are collinear, so we just use power of a point. CE times CA equals CD times CB. And then in addition, this quadrilateral cyclic AEHF, so we use CH times CF equals CE times CA, and similarly for that. So we use this power of a point to show that D prime equals B, E prime equals A, and we're done. Next, inverting a circumcenter. Let ABC be a triangle with circumcenter O. Invert around C with radius 1. Then C and O are reflections about over A prime B prime. This time I'm drawing C at the top. So this radius 1 thing, it's actually not so important. We could just replace it with radius R. This mainly is just an angle chasing problem, right? I don't have much to explain here because the angle chasing is kind of straightforward. O here, that's O. We're gonna draw B prime here, C prime here, say O prime here. Alright, we just use this angle chasing. We know B prime, O prime, A prime is we're directing all angles here. B is B prime, O prime, C prime plus C prime, O prime, A prime, which is directed angle addition. And then using some circumcenter properties that they actually we preserve them through these directed angles. B prime, O prime, C prime is equal to CBO plus OAC in directed angles. And what's okay, and then we use these to CBO is equal to 90 minus BAC. OAC is 90 minus CBA. And then we add these to find this 180 here, and then B prime, A prime, C prime plus C prime, B prime, A prime, we're subtracting, and then we get A prime, C, B prime from some, this is a property of, this is triangle sum angles under directed angles. These angles tell us that CO prime is perpendicular to A prime, B prime, and because we have this B prime, O prime, A prime is equal to A prime, C prime, B prime, we can conclude that C and O prime are actually reflections of A prime, B prime. So that's pretty cool. Proving this might be a little weird. I didn't have so much fun proving this problem because of these weird angles, but it's still not too hard to show. And next, this is our last lemma here. Inverting the incircle. Let ABC be a triangle with circumcircle capital gamma and contact triangle DEF. Consider an inversion with respect to the incircle of triangle ABC. Show that gamma is sent to the 9-point circle of triangle DEF. I'm going to draw a triangle here. This is neater because I'm drawing with my finger. A, B, C. And we'll draw the circumcircle. Actually, it's better in. Oops, sorry about that. It's better when you're drawing a diagram and, for example, in Olympia, to draw, if you're given the circumcircle, draw the circle first and then draw the triangle. So here's D, E, F. Now, this 9-point circle DEF is kind of weird. We don't usually take a 9-point. We don't usually see problems where we take the 9-point circle of indeed a smaller triangle, but it's actually not too bad because note that AE and AF are actually tangent to their incircle. So by our very first theorem, that tangents and inversion theorem, we find that A is actually inverted to A prime over here. A prime, the midpoint of EF, once again, is proved by similar triangles. And also don't forget, it's important that D, E, and F are actually preserved because, you know, they lie on the circle of inversion. A is mapped to A prime. B is mapped to B prime. C is mapped to C prime. These are all the midpoints, okay? So now, circumcircle gamma is going to be, so the circumcircle of ABC is going to be inverted to the circle of A prime, B prime, C prime, okay? So now, the A prime, B prime, C prime is the circumcircle of the midpoints, but by definition, that's the 9-point circle of DEF. So that means we're actually done. Yay. Alright, so now your brain probably hurts. I'm sorry, but here's an example problem. You can put your mind to it and see how it goes. Problem, let ABC be a right triangle with angle C is 90, ABC. Let X and Y be points in the interiors of segments CA, CB, respectively. Construct 4 circles passing through C, centered at A, B, X, Y. Prove that the 4 points lying on exactly 2 of these 4 circles are concyclic. I have an extra slide for work here. So we want to show that this circle is concyclic. This is actually a circle. First, we see this tangency thing and that Y lies on CB, X lies in CA. You can just imagine how helpful this is going to be when we invert through C. Look, we have tangent circles, so not only are X prime and C prime going to be tangent under the inversion, X prime and A prime, sorry, are going to be tangent under the inversion, the circles actually pass through C, so they're going to become lines. We have parallel lines then. Isn't that great? Oh, sorry, that was a bit weird. Anyway, so we have parallel lines here. It's going to be perpendicular to CA here. And then similarly, these are going to be some parallel lines. What does that look like? That looks like a rectangle, man. So, and we have to also note these intersections are going to be preserved. So it turns out these intersections are going to become the vertices of the rectangle that's formed by A prime, the these circles inverses. So let's draw that here. We're gonna have our point C here. Let's say A prime is here. Let's say X prime is here. Something happened. Something weird happened. Oh, all good. Alright. Y prime, B prime. So we're gonna draw in our parallel lines. See this rectangle here. And P is going to be the intersection of circle centered at Y, circle centered at Y and circle centered at A. So it's going to be, P prime is going to be the intersection of Y prime's inverse and A prime's inverse, circles inverses, which is going to be right here. That's P prime. Now similarly, we can draw Q prime, R prime, S prime. Q prime is, what is that? That's X and Y, right? Yeah. X prime and Y prime. Q prime. R prime will be X and B, and then S prime will be A and B. So now, if we want to show that PQRS is cyclic here, we again go back to that theorem 8.7 about clines inverting to clines. We want to show that P prime, Q prime, R prime, S prime is cyclic. But P prime, Q prime, R prime, S prime is just a rectangle, and rectangles are obviously cyclic, so we're done. See how quickly and beautifully inversion killed that problem? Yeah. Let's continue. Even more. You thought it would end here, huh? You thought wrong, man. Inversion has a lot to it. So I'm gonna present two of the most important lemmas that you need in inversion, as well as what you've just learned. This first lemma is important to circles with radii as tangents to the second circle, while the second lemma can be helpful when we're focusing on a triangle ABC. Let's go. First lemma 8.13, which is inverting orthogonal circles. Let omega and gamma be orthogonal circles. So orthogonal circles are where the radii are perpendicular to each other at the intersection points. Let me draw that. Of course, you need to see that. So let's say this is our intersection point. This is the two centers. Then if these circles are orthogonal, then this radius is perpendicular to this radius. So this even gets a special property under inversion. So what do we want to prove? We want to prove that gamma inverts to itself under an inversion through omega. Alright? So here's our proof. Let's say X is this intersection point, right? Okay? And let's say A and B are 2 points on gamma. Say A, and then we'll draw this line to B. So because of this power of a point like definition of inversion, this is just straight power of a point, man. We have OX squared, which is the radius of inversion, is equal to OA times OB by power of a point, right? So A prime is actually B. A is inverted to B, and similarly B is inverted to A. That means each point has its inverse on the circle, so we're essentially just inverting gamma to itself. Isn't that cool? And this is especially helpful when we can invert a diagram such that we're keeping two important entities the same, yet making other parts of the diagram of the problem simplified. That would be really helpful and powerful, right? That's why this lemma is so important. Let's continue. Even more, forced overlaid inversion. This is more commonly known as root BC inversion, followed by reflection over the angle bisector. So let ABC be a triangle. Consider the transformation, which is inversion. Consider the transformation consisting of an inversion about A with radius AB times AC, followed by a reflection around the angle about the angle bisector of angle BAC. This transformation actually fixes B and C. This is actually quite intuitive. We're just going to formalize it a bit. Actually, I'm not going to need it. We need a little more space for showing this. Let's draw over here. Iceberg. Alright. A, B, C, oops, C. We'll draw our angle bisector. Alright, so radius, actually it should be square root AB times AC. Don't worry about that. So square root AB times AC. So what's going to happen to B? Well, since AB times AC is, AB times AC, we're going to have B inverted to a point B prime on ray AB, so that AB prime, the distance AB prime, is equal to AC, alright? So we have that, and then on C prime is going to be over here similarly, because AC prime is equal to AB. Now, it should be pretty straightforward from here. When we're reflecting over this angle bisector, we're going to have some congruent triangles. In fact, let's draw the perpendiculars from B to the angle bisector, C to the angle bisector. So we have a congruent angle here because of angle bisector. We have a congruent side here, and we have a right angle here. Because these are right angles, we actually can find easily that these two are congruent triangles, right? So it turns out these feet are actually the same point, and also because of this, we see congruent triangles. We see that this distance is equal to this distance. So reflecting C prime over to B, reflecting C prime over the angle bisector goes to B. All right. Similarly, B prime goes to C. So we see that ABC is fixed under that. This is very helpful when we have a triangle and an angle bisector, and we see that things might, work well. And we're gonna see, in fact, in our example problems, two problems that use this lemma, and we're about to see them, because we have the inversion distance formula first. So of course we need to know about distances under inversion, especially for these computational problems that you are going to see in problem of the day next week. So let's see. Theorem 8.18. Let A and B be points other than O and consider an inversion about O with radius r, then distance a prime b prime is equal to r squared over OA times OB times AB. Equivalently, AB is equal to r squared over OA prime times OB prime times a prime b prime. So the first part just follows from similar triangles, right? We're gonna have, let's draw that here. Oops. O, A, B, and then A prime, and B prime. We're gonna have this similar triangle OAB, OB prime, A prime. So then we have, what do we have? We have OA prime is equal to r squared over OA, and OB prime is equal to r squared over OB. So we're just multiplying A prime B prime by this similarity ratio we're multiplying it by AB. Okay, so from it should just be pretty easy. Similar triangles and power this length condition. And then the second one, it's just the reverse. We're taking, suppose like this is instead A prime B prime, it's just the same thing. Or you can do a bit of manipulation. I'm using the definition of inversion, r squared over OA prime, so it should be pretty easy also.